Bismillah ar-Rahman rahim. Dear students, we talked about uh, basically what we dealt about was the lines and the flat surfaces. But now today we talk about the curves and surfaces. Okay, we had done like lines or squares or triangles, okay, or circles. They're all flat surfaces, okay. But now we need to talk about the curves and surfaces, okay. Now these flat surfaces basically they fit well with the graphical hardware, because graphical hardware it's easy to draw these kind of figures rather than drawing the complex objects, okay, with lots of surfaces and lots of things to figure it out. But the world is not made up of these guys, rather the world is made up of the curved and curvy surfaces, okay. But uh, does that mean that we have to use some complex implementations? No, implementation will be same, okay. Implementation will be kind of uh, what we use it for the flat primitives, the primitives we use it for the flat surfaces, we'll be using that for these guys also, okay. But at the application level, you have to talk about the surfaces and all, but at the implementation level you will use the flat primitives, okay. Okay, the same flat primitives which can be used recurrently to generate these surfaces and complex real objects, okay, because real objects are very complex. Now what we need to develop, okay, what we need to develop, okay, first will be the representation of curves, okay, representation of curves. The first thing you need to do is the representation of curves, and second thing is tools to render curves. And then these curves will be used to generate the surfaces, okay, the complex surfaces. But first of all, we need to understand what we mean by a curve. So what is a curve? One is a mathematical thing, okay, if we see the mathematical interpretation, and one is what we have come across in the real world, the real world, or I mean say what we do usually. And I'll talk about the curves. Whenever we talk about the curves, it actually means basically something which is curvy, okay, the curvy road, the curvy things, okay, something which has some kind of a curve which we understand by this. But what is technically a curve? It's a mathematical, we need to see it mathematically, what mathematically a curve means. And what is a non-curve then? If something is a curve, what is a non-curve? It seems the line, it's a non-curve, okay. I'm not saying mathematically, what we usually deal with the things in a real world, we say something which is straight, it's not a curvy. For this road is doesn't have a curve, but if the road is like this, it's a curvy road, we say it is curve and it is not a curve. But mathematically this is not true, okay. Mathematically the line is also curved, this is also curved. So what is a curve? First you need to understand, okay, how can we define the curve? A curve can be defined which is having some set of points. We usually call them as the control points, and it need to have the firstly set of points, and it need to have a continuity. The continuity is important because continuity makes it either the non-curve or curve. So the continuity here means that we cannot have the gaps, okay. So what does that mean? Say for example we have these points, 1 2 3 4 points, and I joined them. You see, I take the pen and I'm joining them in a continuous manner, I'm not lifting my pen, okay. So then this is a curve. When we have a set of control points, like these are the control points, okay, and we had no gaps and there was a continuity in it, we need to have no gaps, okay. So this will be the definition of your if you want to say a definition of your uh, this curve, you will say a curve is something which has which is made up of a set of points. Okay, what we say is when we have when we join set of points in a continuous manner without having any gaps, it will be called as a curve. Okay, so if we say the definition of a curve, we can say the set of points, also called as control points, huh? We can call as the control points, okay, which are joined with continuity without having any gaps. So you do not need to have any gaps, then it's a then it's a curve. So by that definition, if we have these 3 points in a straight line, so I'm getting a straight line, and this is also a curve because I am joining, maybe this is only 2 points, okay, and I'm joining, so it's a set of points. I'm not having any gaps, okay. So for example, say for example, I have put up here line, and now I'm not continuous, and I'm drawing a line. So I want to say this whole thing is a curve. I'll say no, this whole thing is not a curve because there is a gap in between. But in a line, if I have 2 points and I'm joining it, I'm having a 2 points. So these are control points. So a curve is having the set of points, the control points. These two also as a control points. Without joined with continuity, so you are joining with continuity, that means I'm not lifting my pen and I'm joining these two, so that's also done. Without having any gaps, I'm not having any gaps, so by that, that means in mathematics straight line is also a curve. Now for example, I started from this point and go here, and I go here and I come back. Now I made a triangle. Okay, now I have some control points. Yes, I have control points. Nice. Is have I done in continuity? Is there any gaps? No, there is no gaps because I went from here to here, then here to here. No gaps, sir. So that means this is also a curve. So that means any polynomial can be a curve. Okay, you can put up a here. Okay, you go for here, like this, maybe like this, and like this. So I made a kite, nice kite. It's also a curve. Okay, now I make a circle. Say I started from this point, I went on, bingo, this is a curve. So then if I'm seeing, it's kind of everything is curve. So if everything is curve, what is then a non-curve? That comes the question in my mind. What's a non-curve then? A non-curve will be which have gaps, where we do not have a continuity. If we do not have a continuity, then that will be called as a non-curve. So what does that mean? We do not have a gap. Okay, firstly, can you tell me, is this a curve? I'm going from here, going from here, going from here, going from here. Is this a curve? Yes, sir, it's a curve. Okay, it's a curve because set of points and continuity. Circle, yes, sir. And I want to make a simile face. Is this a curve? No, this is not a curve. So this is a non-curve. Why is this non-curve? Because there's the gaps. I made a circle. I went from here and here. Then I had to lift my pen and then draw this small circle. Lift my pen, then draw this small circle. So I will say this is not a curve. But if I could make it in continuity like this, then make this, then come here, then make this, then go here, then come here. Okay, make this, then make this, and make this. Now it's kind of a curve because there is no gap. So if we have a gap, then it's not a curve. If we have a continuity, then it is a curve, no matter what you make. Okay, no matter what kind of shape you make. I don't know what shapes you are making. You are doing like this, and you're going here and here and here. In fact, this is called as a complex curve. Okay, and this is called a simple curve when they do not interact, then when they don't have a cross section. But if they have a cross section point, now this is called a complex because you have multiple directions to go from that cross section. You can go this way, you can go this way, you can go this way, you can go this way. But here, if you take any point on this line, you can go only two ways, either this way or this way. There's only two ways. But there, if there is a cross section, okay, then if they're crossing each other, then it can go multiple ways. From that point, you can go multiple ways, right? So anyways, we said there is a curve, okay, if it has a points. Number second, it is continuous, you don't have to lift the pen. Number third, you um, you should not have any gaps, right? Okay. Now curves can be either open or closed. So what is an open curve? So open curve is where we do it but it doesn't come back to it. Okay, see, you make like this, okay, you make like this. It's a now you say there's a gap, but I am making it from here, and this is my end point. Maximum times, it curve is said, if any point you take up, it has a two neighbors, either right neighbor and the left neighbor. Only 2 points which are the end points doesn't have only one neighbor, okay, on the left or on the right. But maximum all the other points have two neighbors, okay. So you started from here, you went here without any gap, you come here, so this is definitely a curve, okay. But closed curve will be like a circle, okay. You make any figure, you want whatever you want to make. So this will be the closed curve, right? A curve which is coming back to it. So this is in fact not only the closing, this is also the crossing curve, where they cross. So if they cross, okay, it's called as a crossing curve. If they do not cross, then it's non-crossing curve. Our question is how to represent these curves, okay. How we gonna represent the curve, how curves are presented, or depending on that we also have the three types of curves or three types of representations. Number one, we have what's called an explicit, okay, representation. Number second, we have what's called as an implicit representation. And number third, we have what's called as a parametric, where we use the parameter, surface parameter, and parametric representation. Okay, so we have implicit, we have explicit, we have implicit, and we have parametric. So what is now the explicit representation? How we represent the curve using explicit representation? So our number one is what is called as an explicit representation. So how we represent explicitly the in explicit representation, what we have is we have a dependent variable and an independent variable. Like we have y is equal to f of x. So where for each value of x, we have exactly the value, some value of y. Okay, only one value of y. For each value of x, we have just a one value of y. Okay, so you can like we had the straight line equation, y is equal to mx plus c, right? So whatever the x value is, okay, and on that slope, if you want to calculate what is the y on that, so you give the value of x, and c and m is given, and for one value of x you will get the y. So if you have this type of representation, and this will be called as an explicit representation, where we have explicitly given one variable, okay, one variable declares explicitly the other variable. That this is why it's called as an explicit representation. But this cannot represent each and everything. Now if we have, for example, vertical line, so this cannot represent all curves, okay. Like we have the vertical lines, like we have the circle, so it cannot represent everything, okay. But we can extend it to 3D, okay. We can add up the z. Say for example, we said y equals to f of x, okay, and maybe g is equal to z is equal to g of x, so you got a z value also here, Okay, so the form we can keep up here is z is equal to f of x comma y. Okay, and this will define me the surface, because surface needs all the three things. So now you want to calculate the z. Okay, you need x and y, but firstly you calculate, you have the x, then by that you calculate the y, and if you have both x and y, you can calculate the z, that's the depth. Okay, and that's the z value, okay, in a space, and that thing will be your surface. Okay, so if you have only x and y, like we said, y is equal to f of x, like this. Okay, because we said y is equal to f of x. Okay, this is for the curve, that we have. For example, this is my x and this is my y, and I have some curve here. So this is the relationship between the x and y to get the curve. So you give some specific value of x to get the y using some equation of this curve, whatever the curve we have. Okay, is it spline, is it some other curve? So you can get, you plug in the x, you will get the y, because y is the function of x. But if you have the three things like g is equal to a function of x comma y, that you give, uh, now you plug in the x and y to get the z things, because now we have the three x's. Okay, this is x, this is y, and maybe this is the z coming out of the screen. Okay, now this will give you some kind of a, you have this kind of a curve, then maybe you also have a here some other the same repetition of some like this. Okay, so that you join them together and to get the surface. Okay, if you have the x and y, you need both of things to calculate the z using some formula, that f is a function of this to get the surface. So this will get the surface. Okay. Okay, now in explicit, what we said is that you need to have some variables, okay, explicitly, to get the another variable, right? Whether it is for the curves or it's for surfaces, right? So if it is for the curve, then you have the, for example, the x to get the y, because we say f y is a function of x. So you plug in x to get the y explicitly, and to get the surface and get the z, you need to plug in the x and y to get exactly the z. This is called as the explicit representation of the curves. Now if you want to get the surface, actually surface is nothing but, if you have some kind of a curve here, for example, and you repeat the same curve, okay, and then you join them together, you get some kind of a surface, right? So basically surface is nothing but a combination of these curves and then joining about these curves together to get a surface. We talk about surfaces more later. Okay, right now I'm just giving the introduction. Now the next is representation is the implicit representation. So in curve representation we say implicit curve representation. So what is the implicit curve representation is here what we represent, okay, 2D curve and a 3D surface, or 2D curve, because curve is on a 2D or 3D surface. Okay, on 3D we have a surface. When you take up the z parameter also, we get a surface. Okay, how we represent 2D curve or a 3D surface as zeros of a formula. If you have zeros of a formula, we can get it, we can say this is an implicit representation. Like for x square plus y square plus z square plus 1 equals to 0, like this. Okay, now here we can have a multiple values. Okay, we can have multiple values you have a same some x value, you can have a multiple y values. Okay, not necessary that you will have, like in a express presentation, each value of x will have only one value of y. Here each value of x can have multiple values of y. Okay, like for example, we have the circle formula, as we have done in the circle formula, x square plus y square minus r square is equal to 0. This was our circle formula. Okay, you can plug in the x, for a particular x we can have different y values also. Okay, so this is one important point here. And because it can represent multi valued curves. And in a simple term, if you want to represent the implicit function, like we said, we said here, in case of our explicit, is that y is equal to f of x. Here you have to say like y equals to f of x is the, in that is my explicit curve representation. But implicit curve, we say like this, it represents as the zeros of a function, right? So how we do that, the zeros of function is f of x comma y equals to 0. So this is our general formula for this. So you can add up any, like this is a circle formula, or we can have a line formula, and we can have any many formulas you like. And if you want to, this is my curve, which is a 2D, but if you want to put it on a 3D, so that is a surface, then you say f of x comma y comma z equals to 0. Now this thing is a general formula, implicit representation of surface. Okay, and this was the implicit representation of curve, and this one is the implicit representation of surface, where we have the z value. And also we need to note down that here only those will be present which can be present in terms of x, y, and z. Like for example, all the lines, if you have all lines can be represented by this formula, where we have ax plus by plus c equals to 0. This is my line formula. And for circles, all circles like x square plus y square minus r square equals to 0. This is the circle representation. Okay, and this one is the implicit representation. And if you want to say for surface, so for surface what you want to do is what should say, f of x y comma z equals to 0, right? So this is the general representation. Explicit, this is the implicit representation of a curve and a surface. Now the third representation is the parametric representation, where we have the parametric curves. Parametric representation, and this one is the third one. Okay, and you should note down that maximum curves are represented by the parametric representation, and what we do maximum times is we use the parametric representation to represent our curves and surfaces. Okay, now what we do here is, in implicit or explicit, we were talking about x in terms of y, or y in terms of x. Okay, or z, depending on the kind of some x and y's. We deal with that. We represent x in terms of y, and y in terms of x, and so on. But here parametric representation represent each spatial arrangement with a spatial parameter, that is the surface parameter or the curve parameter u. Say for example, we call it that parameter as u. Okay, this is a single parameter where everyone will be dependent on. Say for example, if you want to, so you want to represent everything in terms of parameters using the parameter. So for example, you want to represent a 2D curve. So how do you represent 2D curve? Okay, what we have is we will have two functions, two separate functions for x and y, because if you say curve, we need to have x and y. And here if you say explicit, because x is equal to function of y and y is a function of x, and so on. But here what we have is that we will have two separate functions for x and for y, and both of them will be dependent on the u, that's the parameter. Okay, and we will have the two functions for 2D curve. We will have two functions, and we will have one parameter. Okay, like x of u comma y of u. So y of u and x of u. So this will be two functions for x and for y. So we will have a separate equation for each spatial variable. So whatever the spatial variables are, for example, in the curve we have only two, x and y. Okay, but if it is a surface, then we have x and y and z. So we will have a separate equation for each of this spatial variable. Like for example, we say for x it will be like x of u, for y it will be for y of u, and if we talk of surfaces, then z, then we have z of u, right? Right. But here for the curves we have two functions and one parameter. But for 3D surface, if we talk about explicitly 3D surfaces, okay, we will have a two variables, okay, two parameters, I mean to say. We will have definitely the three functions because now the z will come up. So we have three functions, but we will have two parameters. Okay, so say for example this is x of u comma v. Okay, then y of u comma v, so two parameters we have, and z of u comma v. Okay, for example if you want to represent say for example if you have a parametric sphere, for example parametric sphere, SFHERE. So how we will represent it? We have to represent for the x, and we have two parameters here, theta and phi. Okay, and that will be equal to cos phi and cos theta. The x we will get by this, and y, for the y we have a formula theta and phi. There will be two parameters, and for z also the theta and phi, the two parameters, and the formula for the y to find the phi is cos phi sine theta, and for the z we have only sine phi. So this is the parametric representation of a sphere. Okay, okay. And if you wonder what is the phi and theta doing here, because for a sphere, if you want to draw the sphere, we have the longitude and the latitude. One is on this side, there are circles on like this, and there are circles like in this manner. And you say theta here, that is a constant. Okay, theta constant, which is here as a parameter. Okay, that's a circle that present, that's the circles of a constant longitude. And your phi constant, that will be circles of constant latitude, right? All right. Now the last thing we do in this segment is which representation we should choose. Should we choose implicit, should we choose explicit, or should we go for the parametric representation? It depends upon the application basically, okay, which application you're talking about. Okay, now if it is an implicit representation, it's good for computing ray intersection with surfaces. If there is some ray which is intersecting on a surface and you want to calculate that, so maybe its better idea is to have an implicit expression. So you have, for example, some kind of a surface, and some ray is coming up and intersecting on this point, and you want to compute that ray intersection with surface. So better is to use the implicit representation. Or you want to find inside outside point. For example, you have a point, we said inside outside test, we did it last time. Okay, for uh, the hidden surface removal algorithms, we discussed it, inside outside test. For there it is implicit representation is better, right? And parametric representation, it's good for breaking surfaces into small polygonal elements for rendering. You want to like a mesh, you want to divide this into smaller polygons. Okay, you want to divide it into smaller polygons like a mesh. You must have seen some kind of a mesh all over the place to draw the objects. For example, you want to draw a car. Okay, this is my car, and you draw it using some kind of a mesh things. Okay, because you divide the object into some smaller segments. For example, if you see, this is the parametric representation of your sphere, where you have this longitudinal circles and latitude circles. You divide this into smaller polygons. Okay, and here the parametric representation is nice, because as you see here, this parametric representation we discussed it using two parameters, theta and phi, for the longitudes and for the circles of longitude and for the latitude. This is how we represent it. Okay, we kind of a wire mesh where the parametric representation is best to design these objects. Okay, so if you have to break surface in smaller polygon elements for rendering, then parametric is nice. Okay, or you subdivide into smaller patches. And sometimes we convert from one representation into another. We can also interchange from one representation to the other, right? Okay, now in general, if you want to say key which one, which you will use. Okay, so you will try to use that representation. So what representation um, you want? Okay, if I say what representation is best, what representation is best? It definitely depends upon the application, what application you have. Depending upon that, you will choose your like I said, if you want to break your object into smaller objects, or smaller polynomials, or like here in the sphere we divide it into the smaller circles, and then the parametric representation is better. So it depends upon your application, right? What application you have. But no matter what, it should be stable. Okay, it should be smooth. The curves you will draw, they need to be smooth, because sometimes, if this is a if these are the points, okay, so maybe the points were here, they were not on a line. Okay, it's coming up. This is what called approximation algorithm. We'll discuss them later maybe. So maybe you will choose some nearer, so that your curve is nearer to those control points, or that curve is exactly on those control points. Okay, so the more closer and more the points are on the control point, the smoother the curve will be. So you will choose some that representation which is giving us the smooth and stable curves. Not only that, it should be easy to evaluate. Okay, it should be easy to evaluate. Okay, okay. Or and also, like I said, that they must interpolate. Either interpolate. That interpolate means that these points exactly come. So we can say must uh, interpolate. Okay. I mean, either, I mean, not must, I should either interpolate, or uh, get closer to control points. So you have to choose an representation in a manner that exactly interpolates. That means it exactly, the points are exactly on a curve, or they come no, closer to the control points. So you choose that kind of representation, right? So that's all for today. It's a good beginning for this, and you must have cleared two things. So firstly, what is curve, and what is the difference between curve and a surface? And second thing is, what is curve and non-curve, if there's a non-curve, and what is curve, the difference between that, and the last thing is how we represent the curves and surfaces. Okay, so see you next time. Until then, masalam.